Good morning and welcome back to the course. We're talking about the symporter, and we've gone through a detailed exposition about how this works using what you might call the pseudo-equilibrium mindset. And the reason I say that is that we argued that in the spontaneous processes, Gibbs would have us think about them as moving in the direction of increasing the entropy. And we know the terminal privileged state is that state at which that entropy is maximized. A parallel way to say that, this may sound obscure, but I think I tried to make the point, is Gibbs had this brilliant idea that, well, yes, it's true that the system and the reservoir, the whole thing, I put an Eppendorf tube in the ocean. What happens is that the composite entropy of ocean plus Eppendorf tube will maximize. But his thought was, well, that's kind of complicated to keep track of the ocean itself. And instead, if we want, we can replace that original problem with a new problem, which is minimize the free energy of just the stuff in the Eppendorf tube. And so, alternatively, we can imagine the process as going in the direction of trying to reduce the free energy. So we computed the free energy and we worked out our dynamics using the where did I write it down? We wrote down this kind of an equation where we said that the rate of change in the number of sugars on the inside of the cell is given by the rate of the rate of change of the free energy with respect to the number of sugars on the inside. This is really cool because the right-hand side is a hypothesis. It's a hypothesis about kinetics. It's a kinetic hypothesis. Now, what we're going to do is we're going to reformulate our problem dynamically. We're going to no longer use the language of equilibrium and free energies, but instead we'll use the language of rate equations. And these should give us the same insights, but there's also some extra nuance that we can gain by reformulating our problem in this language. So, what I'm interested in, to go back to what we've already said, is we're interested in the situation where we start out, as you can see here, with more ions on the outside than on the inside, and more sugars on the inside than on the outside. And what's going to happen is that over time, the ions are going to go down their gradient, and the sugars are going to go up their gradient. And I think the key thing to keep in mind, to my way of thinking, in a way, the most important thing I can tell you about this impression of Humpty Dumpty putting himself back together again and going back up the wall, the reason that offends our sensibilities so much is that we never see that kind of irreversible reaction. The thing is that here what we're talking about is actually strictly downhill. In other words, because of this all-important coupling, that's the thing that I want to say. The coupling is the key idea. This object, the symporter, is an AND gate. It only permits the reaction to go when both the ion and the sugar are present. If ion is alone, sugar is alone, the thing doesn't go. It doesn't open up. No transport takes place. So the demand is, thou shalt be an AND gate, and when both an ion and a sugar bind, then this thing can actually permit the free energy to get reduced. And what does that mean? It means for one of the molecules, namely the ion, to go down its gradient, and for the other molecule to go up. But together, the net is that the free energy decreases, or the entropy increases. You can say it either way. Okay, so that's what's going on. So we're going to write down the chemical equation that describes this, and in particular, what I'm going to do is I'm going to write everything in terms of the concentration, so our dynamical variables of interest, I'm going to say are Cn, let me see what language I used here. Okay, that's the way I did it, so let me redo this. So this I'm going to call Cs in, Cs out, Ci in, and Ci out. And each one of these is a concentration. So this is the concentration of sugar on the inside. this should give you the notation. This is the concentration of ions outside, etc. Okay, I'm not going to go into all the details. So I want to write down an equation for ds in, and I'm going to follow my nose. So I would call this scratch and sniff. Given the reaction that I show you up here, I'm going to put a K plus here, and then I have a CS out, CI out, minus K minus, and then CS in, CI in. So let's look at what this equation is stating. What it's asserting is that the way we increase the number of sugars on the inside is by this. What does this say? It says you take stuff on the outside, and the rate has got an intrinsic constant, which I've called K plus. But then how often this happens is going to be proportional to how many sugars there are on the outside and on how many ions there are on the outside. And then similarly, I have the back reaction, which I show you here, and that has to do with the fact that that I could go in the backwards direction, and that means taking sugars from the inside and send them back over to the outside, and ditto for the ions. Now, in steady state, we can rewrite this thing. In steady state, this is equal to 0, which tells me that CS in times CI in divided by CS out, CI out is equal to K plus over K minus. And I'm going to put a equilibrium here as a label. And this is equal to 1. Now, how do I know that? I know that because if you go back to what we did earlier, it's right here. If you look at your notes, okay, let me go all the way back and just remind you. So what we said is that the driving force here is given by this beautiful and simple expression, which is basically 4 chemical potentials. Chemical potential, the ions on the outside, the sugar on the outside, the ions on the inside, the sugar on the inside, the sugar on the outside, and, I think I made a mistake. I think I need to have, let's see, yeah, so this guy right here, I should have called in. I'm glad I caught that. That's obnoxious. So what did this thing say? It said that the driving force is given by basically the change in free energy when a single ion and a single sugar move from the outside to the inside. When I do that, the number of sugars and ions on the outside goes down. That means I need to have the negative sign with my chemical potentials, and then for the inside, the number of ions and the number of sugars went up, and that brings me these plus signs that you see right here. Okay, so using the definitions of the chemical potentials, which we worked out once and for all, at least for an ideal solution, I can plug those in, and I can rewrite the driving force in this fashion. The reason that's interesting and important is that I know that at equilibrium, the driving force vanishes. In other words, dF by dN sugar in is equal to 0. When I minimize the free energy with respect to the number of sugars on the inside, the minimum occurs, and that derivative is 0, which means that the driving force has vanished. The only way this is going to be 0 is that if this quantity is 1. Okay, so that's my reason for asserting, as I did down here, that in steady state, these ratios are equal to 1. Cool. So this is also sometimes referred to as the principle of detailed balance. It's an idea, as best I can tell, that was introduced by the famous American chemist Gilbert Newton Lewis, who was a professor at Berkeley, maybe in the 1920s or so. What this asserts is that if I have two states, A and B, then the principle of detailed balance, I'm going to call this KAB, going in this direction, and then this one going in the other direction is KBA. Then detailed balance tells me that PA times KAB is equal to PB times KBA. What does that mean? It means that there's, first of all, there's a steady state, but you also should notice that I can rewrite this as PA over PB is equal to KBA over KAB, and this is also going to be written as e to the minus beta delta epsilon. And so the point I'm making is that when I've reached my steady state, or better yet, when I've reached my state of equilibrium for this thing, then the transitions balance each other, is really the thing that I want to say. And now what we're going to do is this is really where the profundity, if you'll let me use that word, of the so-called biological battery comes into play. So let me just reiterate, why am I so worked up and excited about this biological battery thing? The reason is because I want you to appreciate, I'm sitting in my office at home right now. I have a plug that I'm looking at that has the lamp. It also has one of these outlet things where I can plug in multiple objects. And I have a heater, which you might even be able to hear in the background. I have a phone charger. I have my iPad being charged. I have a computer. I have actually a hard disk for backing up my computer. I have my speakers for my music plugged in. There's a second lamp. And, I could go on and on like this, but what's the point? The point is that over there's something called Southern California Edison. They send us out this universal currency in the form of 110 volts. And then I have these universal three-pronged objects that I can plug in, and I can use it to drive all sorts of stuff. In the other room, the refrigerator's on. That's basically pumping heat from a cold source to a hot source, really against what the second law provides for. But, there is no violation of anything. It's just that nobody said you can't do work, and you can't pay energy in order to pump hot heat from a cold source to a hot source. You can. And so the reason I'm excited here is that, in fact, what's going on is that my little drawing up here was flawed. And the reason it's flawed is because, in fact, what happens is every time an ion goes downhill here, it gets pumped back up again. And so, in fact, the number of ions out and the number of ions in is fixed, and that's the biological battery. We're going to find the same thing for ATP. What do I mean by that? The ratio of ATP to ADP phosphate is fixed. We can draw from that. We plug into that outlet. It's a universal currency, and use it to do all sorts of other things beautifully, as I said for the case of the symporter. Often there's a coupled reaction where ATP hydrolysis goes downhill, some other thing goes apparently uphill, but they are an AND gate. They only can happen together, and in that sense it's downhill. And so what I want to say is that instead of a diagram like this, in fact what's going to happen is that the ion concentrations, these two guys, they're going to be held fixed. Now, the one thing I want to make sure that nobody's worried about, and you should have at least thought of it, is like, well, that seems almost like it violates some law of equilibrium or conservation of energy or something like that to pump the sugar back upstairs. But here's the point. As I told you earlier, the drive here is the delta mu of the proton motive force, if you like. But the sugar is worth 1,000 kTs. The proton motive force is worth 20. So my point is that if the sugar gets across, and then glycolysis takes place, for example, we've now gotten roughly 40 ATPs, and we can burn up one of those to send the pink ion gradient molecule back up so that it can continue to pump. You see what I mean? In other words, the blue molecules, they carry so much energy hidden within them that that energy can be used to drive a reaction, which is to pump the pink guys back up their gradient. So, for our purposes, what this means is that, in fact, there's a new dynamics, and it's and I'm going to call it an effective dynamics. And when I use the word effective, that's comes from physics language. It doesn't mean like good at, like that person's an effective speaker or an effective cook or an effective whatever. I don't mean it in that sense. When we use the word effective in this physics setting, what we're referring to is a coarse-grained theory, a theory that it doesn't account for everything. We knowingly, self-consciously go in with the idea that we're not accounting for everything. It's an effective theory of the world, in the sense that it's a theory that explicitly does not account for everything. So let me write it. So now what I'm going to say is d sugar in dt is equal to k plus effective times cs out minus k minus effective cs in. So note what's happened is that the sugars are the only actors left in the drama. The ions have effectively disappeared. We no longer acknowledge them. So let's see what happens now. So we know that in steady state, in the steady state situation, we have that CS in over CS out is equal to K plus effective over K minus effective, which is equal to now, this is the fun part, that's equal to, that's equal to C ion out over C ion in times K plus bare over K minus bare, right, where bare refers to the original reaction. So this thing essentially represents the broken detailed balance. In other words, I no longer have that the ratio of my rate constants is equal to 1, which they were in the previous case. Let's do one last step of dissection here. So the last thought is to examine this CI out over CI in. Remember that, let's see. So, from earlier we had that mu I out is equal to epsilon solution ion plus kBt log C ion out divided by C naught, and mu I in is equal to epsilon solution ion and then plus kBt log of C ion in divided by C naught. And so this can be used to show me that C ion out is equal, or over C naught is equal to e to the mu ion out minus epsilon solution ion all divided by kBt And similarly, C ion in over C naught. All I'm doing is inverting the chemical potential, if you like, is equal to e to the mu I in minus epsilon solution ion, again divided by kBt. And so the ratio, so thus, Ci out over Ci in has got this really interesting form, which is e to the mu I out minus mu I in divided by kBt. And that is essentially my message, because what we found is that K plus effective over K minus effective was equal to exactly this quantity, mu I out minus mu I in up in this exponential, and then times K plus over K minus. So this is the broken detailed balance factor. And I want you to see that, really what's going on here is that the battery allows us to push the rate constants to values that are different than their equilibrium values. And the point is that by holding the ion concentrations at these fixed out of equilibrium values, namely mu I out minus mu I in, that reaction is not at equilibrium. Because note, if mu I out is equal to mu I in, this prefactor is gone, and we're back to K plus effective is equal to K minus effective, because K plus over K minus is 1. So the drive comes from the fact that we're holding the ion concentrations out of equilibrium, and what that does is it alters the rate constants, pushing more towards the flow towards the inside. So that's really what I wanted to say in this brief vignette, was to comment on this idea of a dynamic. First of all, what are the key points? A dynamical description of the reaction. And when I say dynamical description, what I mean is that instead of using the free energy as our language, we followed our noses and wrote down rate equations. But then we actually noted that the rate equation could be simplified to a new effective equation, and the price we pay, if you like, was that the rate constants in that new rate equation are out of equilibrium, and they're held there because the ion gradient is held at a fixed value. I hope that made sense. Look forward to talking about other stuff shortly.